So it's the same correlations or the same, I guess, procedures in these. We'll go to heat transfer and fluid flow, convection, and then internal flow. Again, let's just look at the average ones. Actually, let's look at the average non-dimensional ones. So what is the functional dependence? We have to know the Reynolds number. So the Reynolds number is the first input. We have to know L over D, that's the third input. We have to know the relative roughness, that's the fourth input. We have to know the duct shape. Again, that is dictated by which of these functions you're calling. And then the additional inputs that we need are the Prandtl number, so that's the second input. And then the thermal boundary conditions. So let's paste this once and look at it. The thermal boundary conditions are kind of hard, actually, right? The two common thermal boundary conditions for which you will find solutions are constant temperature duct and constant heat flux duct, right? And those are the two Nusselt numbers that you get back when you call this procedure. So the first Nusselt number you're getting back here is the Nusselt number you would have if you had a duct that had a constant temperature, and that's what this underscore T means. The second Nusselt number is the one that you would get back if you had a constant heat flux. That's the underscore H, right? So, in all likelihood, your problem is not going to be either one of those two conditions. It rarely is that you have a true, ideally constant temperature or constant heat flux condition, right? You might have something between those two things. But these two solutions are nice to have because they bound the actual solution. So what you're going to find is the constant temperature solution is always going to give you the lower bound on the Nusselt number, and the constant heat flux solution is always going to give you the upper bound. So your solution will lie somewhere in between those two things, and depending on what's going on, you may decide that I'm much more like the constant temperature solution than I am like the constant heat flux, right? Or perhaps you just want to be conservative, in which case you would use the constant temperature solution. But that's where the boundary condition input shows up, right? So yeah, these are nice, I think, in that they sort of organize for you a whole bunch of correlations that otherwise you'd have to be digging through a book to find. But there's nothing magical about these, right? These are literally just finding the best correlations and trying to program them in a way that makes them easily accessible to you. You're not losing any pedagogical value by calling these procedures versus writing the function yourself. Okay. All right, so let's do one last thing here, which is, again, let's look at what the correlations give us and do that with an eye towards remembering how these internal flows behave, right? Because once again, it's not that satisfying when you see something that your model is doing and you ask the question why, and your only answer is, well, that's what the correlation says it should do, right? I mean, you ought to be able to know why the correlation is saying, is behaving the way it is, okay? So what I did here is the same thing that I did previously for the friction factor, and that is I took the limit that L over D goes to infinity. So I'm plotting here the fully developed Nusselt number, which means that I'm way out here where the duct is extremely long, so that the average and the local friction factors approach each other, and L over D is no longer an input anymore, right? So the inputs then are the Reynolds number, the relative roughness, the duct shape, the Prandtl number, and then your thermal boundary conditions, right? So if we come down here and look at these Nusselt number solutions, one thing is you'll see again, right at 2800, you've got a very dramatic shift in behavior, right? And actually, if you want to think about it, everything that matters for a laminar flow doesn't matter for a turbulent flow. Everything that matters for a turbulent flow doesn't matter for a laminar flow. So these two different flow regimes could not behave more differently from one another. If we go over here and look at what matters for a laminar flow, one thing you can see is that Reynolds number doesn't matter, at least in the fully developed region, right? These Nusselt numbers aren't a function of Reynolds number. They aren't a function of Prandtl number. They aren't a function of relative roughness, right? What are they a function of then? These solutions are apparently a function of the duct shape and the thermal boundary condition, right? So why would that be? So let's think about this for a second based on what we know about the temperature distribution for a laminar flow. So in a laminar flow, you've got, again, a gradual temperature gradient that extends all the way across the surface of the duct, right, or the cross section of the duct. The entire duct cross section is experiencing that temperature distribution. So based on that, it's not that surprising, I think, that the shape of the duct, right, the shape of the duct matters. It dictates how sharp or shallow the temperature gradient is. It's also not that surprising that the boundary condition matters, because again, it takes a little bit of time for the duct to sort of react, right? You have to conduct energy all the way to the center in order for it to react to things that happen downstream, okay? So those are the things that matter for a laminar flow. Roughness doesn't matter for the same reason it didn't matter when we were looking at the friction factor, right? It's hard to have roughness elements that are big enough to really disrupt this temperature gradient. Prandtl number and Reynolds number don't matter, at least once you become fully developed, right? And the reason for that is because you have to remember that the heat transfer coefficient is basically dictated by how far do I got to conduct energy. So the heat transfer coefficient then is basically K divided by, for a laminar flow, delta sub T laminar, right? The Nusselt number is H divided by K over D sub H, so we'll plug in H equals K over delta sub T laminar. The K's cancel out, and the Nusselt number, again, is just this length ratio. It's the hydraulic diameter divided by how far do I get to conduct energy, which is something like the laminar boundary layer thickness. Well, in a laminar flow, the laminar boundary layer thickness is some significant fraction of the hydraulic diameter, right? So this number here is going to be something like 2 or maybe a little bit above 2. And you can see, if I go up here, this is a number that's not that different than 2 or 3 or something like that, depending on the duct shape. So how far I got to conduct energy for a laminar flow depends a little bit on the duct shape, right? Because I can smush this temperature gradient out or stretch it, but in the end, it's pretty much dictated by the duct shape. It doesn't depend at all on the Reynolds number, though. Not once you become fully developed, and it doesn't depend at all on the Prandtl number, right? It's a geometric quantity from that standpoint. Now, if we go over and we look at the Nusselt number for turbulent flow, you can see that everything that mattered in a laminar flow doesn't matter in a turbulent flow. So over here, boundary conditions don't matter, the duct shape don't matter, right? Those things don't matter at all for the turbulent flow. You don't see any indication in these different lines of those different parameters. Everything that didn't matter in a laminar flow now matters in a turbulent flow. So what didn't matter in a laminar flow? Well, the Reynolds number didn't matter, right? The Reynolds number matters in a turbulent flow. You can see these lines have some slope to them. So why is that? Well, because in a turbulent flow, how far I have to conduct is no longer a laminar boundary layer. How far I have to conduct is what? It's the viscous sublayer thickness. And the viscous sublayer thickness is actually dependent on the Reynolds number. If I have a higher Reynolds number, I'm going to thin out the viscous sublayer. I'm going to have a higher heat transfer coefficient and a higher Nusselt number, right? What else didn't matter in a laminar flow? The roughness, right? The roughness didn't matter in a laminar flow. The roughness matters in a turbulent flow, right? These different lines have different roughness, and that's because it's pretty easy to have roughness elements in a turbulent flow that are large enough, and by large enough I mean on the same size as the viscous sublayer, to disrupt this temperature gradient and have a pretty substantial impact on the heat transfer. Prandtl number. Prandtl number didn't matter for a laminar flow. Prandtl number matters a lot for a turbulent flow, and the reason is the reasons we talked about before. The Prandtl number basically dictates how thick and how conductive that viscous sublayer is. If you have a Prandtl number that's large, you're basically saying it's got a high viscosity, so it's going to be thick, and it's got a low conductivity. It's going to be a pretty big resistance then to conduction across that viscous sublayer. On the other hand, duct shape doesn't matter, because no matter what the duct shape is, you're still only really talking about the viscous sublayer thickness setting the temperature gradient, and also boundary conditions don't matter, because whatever the boundary conditions are, it takes almost no time for the information to travel across that viscous sublayer. So what happened downstream really doesn't matter very much in terms of what's going on, at any location in the duct. So just some things to keep in mind as you're using these correlations. The behavior of the correlations ought to reflect the physical situation you're trying to model, and you ought to understand that linkage. Otherwise, you're going to have troubles as you're going through a design process, trying to make good decisions in terms of how to design a thermal device. So in the next lecture, we'll actually just basically do an example, and the example will use these correlations in order to solve an engineering problem, so that you can see how to do that in sort of not real life, I guess, but in a semi-realistic way.